Welcome back, organic chemists. Time to finish out some resonance. All right, let's go back to the handout. All right. So the last topic we really need to delve into before we do a big review is ions and the heterocyclics. So we were talking about just generic aromaticity. But the only thing we've looked at so far is those carbon ring families called the annulines. So we are now going to say, hey, could something possibly become an ion and meet those conditions? And the answer is absolutely yes. So for the ions, let's go through the rules. You still have to be cyclic, still have to be planar, still have to be conjugated, and still have to have the Hugel number. All right, so let's try cyclopropene. All right, so here is wonderful cyclopropene. All right, so we've already seen that cyclopropene is not, but my question to you is, what if I made it an ion? Okay, so this sp3 group right here, I'm not saying it would be easy, but what happens if I made it positive? Or what happens if I made it negative? All right, let's take a look at that. All right, are they cyclic? Yes. Are they planar? Well, let's look at this one. When you become a carbocation, oh, okay, so to the answer to that one is yes, you are planar. Are you, or sorry, are you uh conjugated? So we have p orbitals on all of them. And so that just leaves, do I have the correct number of Hugel electrons? So 4n plus 2, change colors here. The key is counting those pi system electrons. And in this case, there's 2. It's going to become a little interesting here in a few minutes. So 4n equals 0. Sorry, 0 doesn't count. All right, and then we also know there's a lot of problems with the 3-membered ring. It just has so much strain. It just has so much strain. But it was an interesting question. All right, how about if I make it negative, though? I mean, it still has the strain. Now, here is the interesting thing about these molecules. Aromatic is so powerful that if it can become aromatic, it will tweak things. It'll tweak things. So the reason I'm saying that is let's take a look at this one. This is still sp3 hybridized. Okay, it is still sp3 hybridized, but it does have a lone pair. So there is the potential of that lone pair going into a p orbital instead of having the sp3 hybridization. Whoa, Jolly, you said that when there's 4. Yes, but this is a special case because if nature can get into an aromatic state, and I like to phrase it, it will pay the cost of converting out of an sp3 and into an sp2 because the overall benefit is so great that it's worth that little cost of energy. Okay, so let's see if this one is worth the cost of energy. So yes, let's assume that that went planar, so therefore it is conjugated. Let's check those Hugel. Was it worth it? And now those and those are in the pi system. So we have 4. So 4n plus 2. Oops, just did that. We're supposed to do math here. So the 4n equals 2. So n equals, oh, 1/2. Frowny face, frowny face. Oh, hey, that looks like a frowny face anyway. So no, this one for our cyclopropene there's just nothing that we can do that will make it aromatic. And so we're just going to, nope, on that one. But what about cyclopentadiene? I'm going to go over to my whiteboard. Interesting question. All right, cyclopentadiene. All right, the question is, can I do anything to it as far as ions are concerned to make it aromatic? So let's first make a carbocation. I'm not saying it would be easy, but let's just take a look at it. And then, all right. So condition number one, are you cyclic? Yes, yes, yes. Condition number two, are you planar? No. Okay, so now the question is here. Carbocations are sp2 hybridized. Woohoo! Yes. Okay. Oh, remember, if nature will pay the cost, nature will pay the cost, that one can go planar. So we're going to put a little if there. All right. Three, are you conjugated? Don't even have to finish that one because it's not even um, in a conjugated system. It's not even planar. So here, are you conjugated? Yes. And yes. So we are to the last question. Do you have the correct number of electrons? Right now I've drawn all over this, but 4n plus 2 is equal to, there's two of them and 2. So we have an overall 4. So 4n equals 2 and n equals 1.5. So that one doesn't work because it didn't get us anywhere. Okay. Well, let's check you. Over here, and remember that lone pair would jump and be in the P system. So 4n plus 2 is equal to 6. So 4n, oh ho ho, yay! This one, if it can go into that state, would become aromatic. And so will nature pay the cost for it to become an sp2 hybridized hybrid carbon right there? The answer is yes, because there is an overall benefit. In fact, we can tell that because of the acidity. Okay, in order to make that carbanion, it has to become negative. The pKa of those hydrogens should be, they're in an allylic location, but they're alkanes. So I would say a little bit less than, maybe in the 50s, 40s, but experimentally, their pKa's are clear down in the 15s because if it was to lose that hydrogen, it would become aromatic. Yay! And so that is a physical characteristic that is shown for the aromatic properties. All right, so we have seen cyclopropene, we've seen cyclopentadiene, and oh, can it get even larger? Well, let's check. No room there. Yep, I'll have to go back to the whiteboard. Goodbye, cyclopentene. All right. Well, 1, 2, 3, 4, 5, 6, 7. Hey, that wasn't too bad. All right, this one is going to have the same issue. So right here we have 2 hydrogens. So it's sp3 hybridized. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, so let's check these. So we already know that they were not aromatic to start with. So I'm not going to go through the check again. We're just going to look about will the ions actually help here. So let's go with the P system. The answer is yes. Okay, I like the carbocation because I am now perfectly conjugated. And let's check the electrons. Oh, that looks like a good number of electrons. 4n plus 2 is equal to 6. So 4n equals 4. So n equals 1. Yay! Okay, if it becomes positive, so this is called the tropylium. And I probably just slaughtered that spelling, but that's the tropylium ion. Very, 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 very stable in nature. In fact, it's often drawn 3, 5, 6, 7, just with the positive in the center, because of course it's delocalized. All right, I love the positive. Let's go for the negative. Am I conjugated? If, okay, I'm going to put that big if right there. If nature pays the cost. Okay, looks like I'm conjugated. I just have to check my electrons. And in this case, I have 2, 4, 6, and 8. Not looking good. No. So becoming an anion did not help the seven-membered system, but becoming the cation did. Oh, look at that. Do ions actually make a difference? So yes, but remember, we're not used to thinking of those sp3 hybridized shifting into an sp2 state. So don't forget that when you're considering the ions. All right, let's go back. And then, of course, I just did all of these examples for you, but since that's not written hopefully on your original, you can go and actually try those again. So it's a great exercise every time you get an answer of, no, I am not, okay, and so a non-aromatic, ask yourself, what if I became ionic? All right, the last thing we need to talk about in this section is the heterocyclics, but I will actually do that in a different video. So until next time, Jolly out.